Here's an example of gas law, in particular the ideal gas law stoichiometry calculation using standard temperature and pressure conditions. So first let's take a look at this reaction. We've got ethane combusting in the presence of oxygen to produce CO2 and H2O. This is a traditional combustion reaction of a hydrocarbon. Okay, we want to always make sure that our reaction is balanced. Okay, and we've got that 2, 7, 4, and 6 are our coefficients. Okay, as we read this problem, I want you to get into the habit of labeling the variables, the values, because with gas law calculations, there are quite a few values present. You're going to have volume, pressure, temperature, moles, a universal gas constant. Okay, you're going to have a lot of values to keep up with, so it's nice if you'll go ahead and label them as you read the problem. So how many milliliters of ethane? How many milliliters is a volume that we are looking for? So we're looking for the V of ethane at standard temperature and pressure conditions. So that means that temperature is 273.15 Kelvin. Pressure is going to be 1 atmosphere. That's standard temperature and pressure conditions. Are required to produce 22 grams. Okay, that is a mass. Don't get that confused with moles. That's a mass of carbon dioxide. Okay, and carbon dioxide is CO2. Okay, so we've got everything labeled now. And we are looking for volume is what we're looking for. Well, let's set up the ideal gas law equation. PV equals nRT. Let's substitute in the values that we were given. Pressure is 1 atmosphere. Volume is unknown. Moles is unknown. R is the universal gas constant, 0.08206. Now I'm not going to put the units here. It's liters, atmospheres per mole Kelvin. And then the temperature, because this is standard temperature, is 273.15 Kelvin. Okay? So we have that. Now on this equation, we've got 2 unknowns that we've got to figure out. Well, there's one value, the 22 grams, that we did not put into the equation anywhere. Okay. Let's, on a side, let's convert that 22 grams of CO2 into moles. Then we will have an N value, and we can solve for volume. Rather simple. Okay, so 22 grams of CO2. I like to set up my conversion factor, my dimensional analysis here. So I have 1 mole of CO2. And remember, we get molar masses by looking at the periodic table. We get the mass number of carbon, which is 12.011 grams per mole of carbon. Oxygen is 15.9994 grams per mole of oxygen. Now we're going to have 2 of those, okay, because this is CO2. Okay, so just a little reminder, subscripts inside of a chemical formula tell me how many moles of that particular element are present, so don't be alarmed by that. Okay, so we add those values up, and we're going to come up with about 44. Now I'm going to do some rounding here on sig figs. Okay, so I've got the 2 times 15.9994 plus the 12.011. Okay, you noticed that the carbon was 3 sig figs here in the decimal, 2 integers. We have a total of 5 sig figs, and with the oxygen we have 6. So my final answer here, I'm going to need to round to 5 sig figs. So we've got 44.010, it looks like, as our molar mass of carbon dioxide. Okay, so we can put that right here, 44.010 grams. Okay, and then we can solve for moles. And again, I'm going to go 2 sig figs because of this 22, so I'm going to end up with 0.50 moles of CO2, a half a mole. Okay, now this is an N, so it can go right there. Okay, so let's go ahead and substitute that in, 0.50. Okay, now we can simply solve for volume. Okay, remember this is standard temperature and pressure conditions, 0.5 times 0.08206 times 273.15. We come up with, again, I'm going to go 2 sig figs because this 1 atmosphere being a standard value. I'm taking my 2 sig figs off of this 0.50. So I have 11, and if I wanted to carry a decimal, 2, okay, but that's not really there. Okay, this is liters. Volume is in liters, but now notice the question was milliliters. Okay, so let's just remember our metric conversions. 1 liter is 1,000 milliliters. So if I have this 11.2, so to say, liters, then I would have roughly 11,200 milliliters. Okay. All right. Now I want to show you one little thing. When it says STP, at STP, 1 mole of any gas has a volume of 22.4 liters. Okay, this is a nice little add-on that you may want to memorize. At STP, it has to be at STP conditions, 1 mole of any gas has a volume of 22.4 liters. So a second way we could have solved this problem is do our mole conversion right here, get the 0.50 moles, and then just simply do 0.50 moles of CO2 and the conversion that 1 mole of any gas has a volume of 22.4 liters at STP, and we would have gotten our 11.2 liters. Okay, we would have gotten that same value. Okay, but this conversion here only works when you're at STP conditions. You can always solve using the ideal gas law, but at STP there's a little bit of a shortcut that you might want to take.